In this video and the next one, we'll be talking about our final topic, which is going to be zeros of analytic functions. So in this video, we'll be talking about the argument principle. So let's begin by talking about a different theorem, and we'll lead up at the very end to the argument principle and then do an example based on that. Okay, so we're going to say let f be a function analytic on a domain D, except at a finite number of poles. Okay, so I've drawn a little picture here to go with all the blue text. So our domain D is going to be this green dotted line and everything inside the green dotted line. And we're going to have all the poles be W1, W2, W3. Okay, so W is going to represent poles, and Z's will represent zeros of our function. So it's not analytic at any of these blue poles, but it's analytic everywhere else on the domain. Okay, so let's continue. So let gamma be a piecewise, simple, closed, smooth curve in D with inside in D. So the gamma here I've drawn is brown, and it meets all those criteria. It's fully inside D with its inside fully in D. Okay, and furthermore, it passes through no zero or pole of f. So notice it doesn't pass through any of these pink or blue points right here, which is key. And we'll say that the zeros of f are, the distinct zeros of f are given by z sub 1 to z sub n, and the distinct poles of f are given by w sub 1 to w sub m. So the key word here I've underlined is distinct. Okay, so distinct means that we're just covering the each of the poles that are different and each of the zeros that are different. So for example, if you have a zero of order 2, okay, let's say that it's of order 2, you're not going to count it twice here. We're just listing the distinct ones. We'll take order into account in just a second. Okay, so now let's talk first about the zeros, and we'll do a symmetrical discussion about the poles. So let's say n sub j is the order of the zero of f at z sub j, where j is 1 through n, so all of these zeros right here. So just as an example, pretend the order here, pretend n sub j, n sub 1, for example, was, let's say, 2. And let's say z sub j was 1 plus I. So this is a 0, and it has order 2. And let's just remind ourselves, what does order mean? That means if you plug this into the original equation, into the original function, then it's going to be 0. So f of this is going to be 0. And if you take f prime of this, it's also going to be 0. But since the order is 2, when you take f double prime of this, it's not 0, okay? And that's the key thing about what order means when we're talking about zeros. That's what the order of a 0 means. So then we can say f of z equals z minus z sub j to the power of n sub j times g sub j of z. So let's analyze what this means really fast. So here's our function, and by saying that it has a 0 of order n sub j, we're saying that it can be written in this form. And let me show you why this is why we can write f of z in this form. Let's take the derivative. So I've taken the derivative, I've expanded up here using the product rule. So let's plug in z sub j into here. If I plug in z sub j into here, then this term right here, this much, becomes 0, which makes the whole thing 0. Okay, now if I plug in z sub j into here, what happens? So we have this term right here, again. As long as n sub j is not 1, then this term becomes 0, which means this whole term becomes 0. And if I plug in z sub j into here, then again this term becomes 0 as we had before, and the whole thing becomes 0. So f prime of z is again 0. And that just keeps happening. So what happens if we take the n sub jth derivative? Okay, so now we're taking the the n sub jth derivative of f, and we're evaluating it at z sub j. Okay, so now what happens? So we just keep going like that, and all we have to pay attention to is this first term right here. This term that right now in the first derivative, it's n sub j times z minus z sub j to the power of n sub j minus 1 times g sub j z. Okay, so I know this is kind of a lot of j's floating around, but try to keep everything straight. So what does this term become? So the next time we take a derivative, we would have to bring this n sub j minus 1 down, and then we would have to reduce this as n sub j minus 2. Okay, and then we just do that over and over again. And when we finally get to the n sub jth derivative, then this exponent becomes a 0, and the first term is going to be n sub j times n sub j minus 1 times n sub j minus 2 all the way to 1. So it's really going to be n sub j factorial. And this term right here always stays how it is, g sub j of z. This stays how it is, and we plug in z sub j into here, and this is not equal to 0, right? Because that's what having an order of value of n sub j means. It means that when you take the n sub jth derivative and you plug in z sub j into here, it's not 0. So we know that n sub j factorial is not 0 because you can't have any factorial equals 0. So that means that g sub j of z sub j is not equal to 0 either, because if it were, then this would be 0, which it's not. So that means g sub j of z sub j is not equal to 0. So that's why, because this all works out, because this all logically flows and it meets the criterion needed for an order of n sub j, we're allowed to write f of z in this form. Okay, so now let's get into let's consider something. Let's see what happens if we do f prime of z over f of z. So I've written out f prime of z on the top, f of z on the bottom, and I've reduced it. Okay, so I reduced it as into this form, and this form we get just by canceling denominators and numerators and stuff like that. And then what I want to do now, I want to put it back as a single fraction. Okay, so now we have this fraction here with a common denominator. And next thing I want to find the residue of this function, f prime over f, which is right here, at z sub j. Okay, so we know that this has an isolated singularity there, because if we plug in f of z sub j, we get 0. And if since 0 is a denominator, we know this has a pole, or some kind of isolated singularity there. So now what happens when I do that? So again, we're just going to do the simple thing where we pick a suitable denominator, suitable numerator, and we do that formula we've already done a couple times, where we plug in z sub j into the numerator, and we take the derivative of the denominator and we plug in z sub j into there. So we're going to choose all this right here that I'm putting in this gray box as the numerator, and we're going to choose this as the denominator. So notice the numerator, there's no problems there, because the only problem would happen if this g sub j of z became 0. But on the back, we just verified for good reason that g sub j of z sub j is not equal to 0. So the denominator of this numerator will not become 0, and we'll have no problems. So we'll be able to plug everything in, and when we plug everything in, cancel out like terms, we're going to get n sub j. So that's great. We know that the residue of f prime over f at z sub j is equal to n sub j. And what is n sub j? N sub j is the order of the 0 at z sub j of f. Okay, so of the function f. So now we're going to do a similar discussion about the poles. So remember, each pole is given by w sub k. So we see that each of the poles here, w sub 1, w sub 2, and so on, all the way to w sub m. Okay, so that's all the poles. So now look with the zeros, we're going to say that m sub k is the order of the pole of f at w sub k. So the order of a pole is a little bit different than the order of a 0, but it's not that much different. So remember, the order of a pole is basically the exponent right here. When we write f of z in this form, we write it as h sub k of z over z minus w sub k to the power of m sub k, and this will be the order of the pole. And remember, we can always write something with a pole in this form, as we showed before. And further, we know that h sub k of w sub k is not equal to 0. We showed that before as well. So now we're going to do the same discussion. We're going to take f prime of z over f of z, and we're going to get this. Function right here, which is an analog to when we got this function right here, because they look pretty similar. Okay, so and then if we take the residue, we basically go through all these same steps. Much of this cancellation is similar. We pick a suitable numerator, pick a suitable denominator, and go on like that, and we get the residue of f prime over f at w sub k at this pole is equal to negative m sub k. And we know that w sub k is an isolated singularity of this function. Why? Because if we plug in w sub k into the denominator here, this denominator, which is f, is undefined, and having an undefined denominator is also something that can cause an isolated singularity. So when we do all the algebra here, we're going to get negative m sub k. So notice that we get negative m sub k when we take the residue of a pole, and we get n sub j when we get the residue of a 0 of f. Okay, so if any of this was confusing, go back, look over it a few times, and now we're just going to give the final result here. So now by the residue theorem, let's say we want the integral of f prime over f around that curve gamma. So just to remind, that curve gamma was right here. It's something that circles a few of the poles or zeros, but doesn't actually go through any of them. Okay, so that by residue theorem is equal to 2 pi I, sum of the residues of f prime over f that are inside that gamma. Okay, so we only have to worry about the ones that are inside gamma. We don't worry about the ones that are outside, obviously. Okay, so we say that residues for f prime over f come from singularities of two types. The first type is going to be zeros of f of z, because that's going to cause the denominator here to be 0. The next type is going to be poles of f or z, because that's going to cause the denominator here to become undefined. Okay, so that's the two types of ways you can get singularities there. So that means that if we want this integral, it's going to be 2 pi I sum of the residues of the zeros plus the sum of the residues of the poles, because that's the two types of isolated singularities we're worried about. Well, what is the sum of the residues of the poles? We just found over here that the residue of a pole is going to be negative m sub k. So if we just add up all those negative m sub k's, then we're going to get the sum of the residues of the poles, and sum of the residues of 0 is the sum of all of the n sub j's. So remember, this negative sign is here because each pole's residue is negative m sub k. So we're adding all of these up, multiplying by 2 pi I. Okay, so the final thing we want to do, we want to take this 2 pi I and move it to the other side. So we're going to have 1 over 2 pi I times the integral in question equals what? So let's just notice something here. What is this quantity right here? This sum from j equals 1 to n of n sub j. So n sub j was what? It was the order of each 0, which is kind of like saying it's the same thing as the multiplicity of each 0. For example, if you remember from just simple algebra, if we have f of x equals x minus 1 squared. Let's say we have that function. Obviously putting x equals 1 in here is going to cause that to be a 0. So it's going to be, we're going to say x equals 1 is a 0. But it's a 0 of order what? It's a 0 of order 2 because we can, basically we used to put off this exponent here. But the same rule applies because if we take the derivative of this, we're going to get 2x minus 1 and that causes that to be 0 as well. But if we take the derivative of this, we're just going to get 2, but it doesn't cause that to be 0. So again, order is just another way of saying multiplicity. So what we say is that we're going to call this right here that I put in the pink bracket as the number of zeros of f in gamma, but you have to be careful of this red statement down here. Remember to take each 0 and pole, we'll see in a second, take their order or multiplicity into account, because the number of zeros, even if there's, as this function, we could say there's just 1 0, but it has multiplicity 2. So we have to make sure we put a 2 here. This would be 2, right? Because it would be, n sub j would be 2. And the same thing here. We sum from k equals 1 to m of m sub k. And this is going to be the sum of the multiplicities or orders of all of the poles. But remember, you have to take the orders into account. If there's a pole of order 5, you need to put 5 there instead of just 1 for that one pole. So in the end, what we have is 1 over 2 pi I times the integral of over gamma of f prime over f dz is equal to the number of zeros of f in gamma minus the number of poles of f in gamma. And we just keep going with this, and we're going to see this becomes the argument principle, something that's very, very powerful. So let's go ahead and do the next thing. So we're going to let gamma of t, before we just let gamma be whatever, I just put it as some free-form weird curve. Now we're going to give it a definite formula. It's going to help us later on. So we're going to say gamma of t is going to be z naught plus r e to the it. Z naught is the center of the circle and r is the radius. So this is, gamma is now a circle, and t goes from 0 to 2 pi, so it's the full circle. Okay, so now we know that f is not equal to 0 on gamma. How do we know that? Because we know that gamma doesn't run through any of the zeros of f, so that means that it's not 0 on gamma. So that means there exists an analysis region where the lower radius, the inside radius, is r minus some small delta, and the upper radius is going to be r plus some small delta. So the motivation behind that is, pretend this is our gamma, right? It's a circle. And we know that on this circle, we don't have any zeros. So that means pretend there's a 0 right here. It's really, really close. That means we can still choose an endless domain. We can still make, if we make this bigger, let's pretend here's that arc of the circle, and here's that singularity, or that 0 we want to avoid. We can still choose a upper bound for our endless ring that's just short of it, and we can choose an inner bound that's just short of it too. Maybe we just avoided another 0 right here. So basically, because of how numbers work, again, numbers are not right next to each other, they have infinite gaps in between. We can always choose an endless domain that's going to work for us, and the endless domain is defined by this expression right here. Okay? So D is that domain. D is going to be our endless domain. So there's a very special note about D. D is indeed that endless domain, but notice something. We're going to let the theta, theta will only go from 0 to 2 pi, not inclusive. It's not going to include 0 or 2 pi. What does that mean? Well, it means it's this whole endless domain right here, but this little segment I've drawn right here is not included in that domain, and that's very important because that means D is simply connected. Do you remember what simply connected meant? Simply connected meant that if we draw a curve that's fully inside, a closed curve that's fully inside our domain, then the inside of that curve also lies in that domain. Now, we said before the problem with endless domains, pretend this was a endless domain right here, the problem was that we can easily defy this condition by just drawing a closed curve that circles that inside, because now inside that curve is something that's not inside the domain. But here, this is not a true endless domain. We've actually removed that part right here. And by doing that, we can no longer draw that red ring, because by drawing that red ring, we're actually drawing one portion of it that's not inside the endless domain at all, the portion that would be right here. So we've kind of cleverly made an endless domain, but made it simply connected at the same time. Now, it's very important that we have D simply connected, because that means that if we have a simply connected domain, like D is, and if we have a function that's analytic on that domain, and f prime over f is analytic on that domain, because we don't have any problems, because f is never 0 on that domain, and f is never undefined on that domain either, because that domain doesn't contain any zeros or poles of f. We constructed it that way. So since that's true, since it's analytic on that simply connected domain, it has an antiderivative on that domain. That's a theorem we proved a few videos ago. So the antiderivative of f prime over f is what? it's going to be log f, because if we take the derivative of log f, it's going to be 1 over f times f prime by chain rule. So that means there's a function h, we're going to name it h, equals log f, which is the antiderivative of f prime over f inside D. So there's a function like that inside D. So I've taken the remainder of the information on the previous page and rephrased it on this new page because I wanted to say it in a little bit different and better way. So it's all the same information, I've just put it in a better format right here. So again, let's recap what we have. We have this analyst domain. Well, it's almost an analyst because we removed this segment that represents 0 and 2 pi angle. Now we have, since this is simply connected domain, we have a function h that's analytic on this domain, where h equals log f and h prime equals f prime over f, which is a function that we're interested in. And now the key fact here is that h is analytic on D and only on D. We don't know if it's analytic on anything out of D, and especially this black segment right here, we don't know if it's analytic there. Okay, so the next step we want to do is evaluate this integral again. The integral of f prime z over f of z dz around this curve gamma. And what's gamma? Gamma of t is going to be z naught plus r e to the it as t goes from 0 to 2 pi, where 0 and 2 pi are included. So again, it's the circle that lies in the center of this analyst domain right here. Okay, so our next step is going to be to parameterize this. We want to take all these z's and replace them with something in terms of t, and that also means taking this dz and writing it in terms of dt. So we're going to do that right here. So the first step we're going to do before we do that is going to be f prime over f. Again, we said was h prime. So we're going to go ahead and plug in h prime there, and now we'll begin parameterizing. So h prime of z, and for this z, we'll plug in z naught plus r e to the it, which I've done right here. And then we need to put dz, and dz is going to be replaced with ir e to the it dt. Okay, I know it's messy, so let me just write it what dz is. So we have dz dt equals ir e to the it. And that's exactly what we get just by taking the derivative of z with respect to t. So then if we want just dz, we would multiply by dt on both sides, and then we would get this expression right here. So now we have an integral here that's in respect with respect to only t. So that's good. Now we can come back to this even further, because look what we have here. We have h prime of this quantity times ir e to the it dt. And what is ir e to the it? That's going to be the derivative of this quantity right here with respect to t. So we can compact this. We can write this as integral from 0 to 2 pi. Remember that we have changed the limits now because the limits of gamma in respect to t were 0 and 2 pi. Integral from 0 to 2 pi d dt of h of z naught plus r e to the it. And why is that equivalent to this? Let's take the derivative. So if you take the derivative of this h of z naught plus r e to the it, you get h prime of z naught plus r e to the it, which is the first thing we have right here underlined in purple. And by chain rule, you need to take the derivative of the inside right here, this purple underlined. And when you take the derivative of that, you get ir e to the it dt. Okay, so that shows that we have in fact written this integral correctly and a more compact form. But there's one thing we did not do correctly. Even though everything we did with the integrand is fine, this limits right here, so these limits that are from 0 to 2 pi, there's a problem. There's a slight problem here that will be problematic if we don't correct it right now. So let's notice something I said in the very beginning here. H is analytic only on D. So everything was fine until we introduced H. Now since we're using H prime here, we're using H and H prime here. Since we're using H prime here, we have to make this integral in a way H friendly, and that's a way to put it. By H friendly, I mean that you can't make it on any domain or any range that where H is not analytic, because we're dealing with H prime as our integrand here, which we transformed using this method here. So since we're going from 0 to 2 pi, we're going from this black segment back to itself, and we can't go from 0 back to the black segment because we don't know what happens in the black segment to H. We only know that it's analytic on everywhere else on this analyst domain right here. So what we need to do a little bit of trickery. Instead of taking the integral from 0 to 2 pi, what we need to do is take a limit. We need to take the limit as epsilon approaches 0 of integral epsilon to 2 pi minus epsilon, and this quantity here is the same exact quantity that we had in the previous integral right here, okay? Now, let me just say a little bit further on why we had to do this. So let's see what this happens. As epsilon approaches 0, what does the lower limit go to? It goes to 0, right? So the lower limit is approaching our starting point that we initially wanted. What's the upper limit going to? 2 pi minus epsilon approaches 2 pi when epsilon approaches 0. So the upper limit is approaching that final point that we really want. So what happens is if this integral converges, so if this limit here converges, then we have actually found this integral right here, because if it converges, then we can define this integral here as the limit as epsilon approaches 0 of this integral here. But we also satisfy the h prime condition, where we never actually go to that black segment right there, and thereby we don't defy anything that h is analytic on D. We're okay with h, and we're okay with the integral. So we kind of satisfy both at once, so this kind of a mathematical trickery. So let's go ahead and evaluate. So we're going to take the limit as epsilon approaches 0 at the very end. Right now, let's just focus on this integral with this new limits, okay? So now the nice thing is that we have d dt, so we have the derivative of some function right here, and we have the integral of a function right here. So if you have the integral of a derivative, fundamental theorem of calculus, and yes, we can use that because this is a real valued integral, because we have a real variable right here. We have t, because before we had dz, which was a complex variable, and we haven't defined any fundamental theorem of calculus for complex variables yet. We do have fundamental theorem of real variables, and since this is a real variable right here, t, we can go ahead and use that. So integral of a derivative means you can just take the function inside of there and evaluate it at the endpoint minus the evaluation at the starting point. So our function inside is going to be this h function right here. So we're going to go ahead and put in 2 pi minus epsilon for t first. So we have h of z naught plus r e to the I 2 pi minus epsilon, and subtract that from h at the starting point. And the starting point was going to be epsilon. So we have z naught plus r e to the I epsilon. Okay, so now we have this nicer quantity. No integrals, no derivatives. So everything's kind of getting cleaned up here. And then h, again, we said was what? H equals log f. So we're going to replace h with log f. Now we have log f of that quantity, the ending point, minus log f of the beginning point quantity. And now what we're going to do, we're going to rewrite this using our log, because we know that log z, any log of any complex variable, equals natural log of the modulus of z plus I theta, where theta is the angle that this z makes with the real axis here. Okay, so I'll do that here. So again, I've written the I've written the log statement right here, and then I've split it up into 4 separate quantities. So let's number 1 and 2 represent what this first part comes from, and number 3 and 4 represent the log at the beginning point. Okay, so let's just go ahead and make sure I did everything correctly. So the beginning log, we're going to have natural log of the modulus of the interior. What's the interior? It's f of z naught plus r e to the I 2 pi minus epsilon. So I've written that here, plus I theta. And now since there's 2 thetas, to distinguish them, I put little subscripts between them. Under this theta, I've written it's the theta associated with this complex number here, with the complex number f of z naught plus r e to the I 2 pi minus epsilon. Now subtract from that, you have to subtract from that this quantity right here. Okay, so how do we do that? We take the natural log of the inside, which is again this, and then you subtract I theta, and this theta subscript is the f at the starting point. Okay, so this is seeming very complicated right now, but we're going to see that some nice stuff cancels out. Now we're finally going to let epsilon approach 0. Okay, so remember, we had to do that from the beginning. So epsilon is now going to approach 0. Let's see what happens to 1 and 3. Well, as epsilon approaches 0, this becomes r e to the I 2 pi, right? So we have r e to the I 2 pi. And what is e to the 2 pi I? It's just going to be 1. So this really approaches r. So what this approaches is f of z naught plus r. Now what about 3? What does that approach? It approaches z naught plus r e to the I. And as epsilon approaches 0, this approaches 0. So we have e to the 0, which is 1. So this also approaches z naught plus r. So if they're both approaching z naught plus r, and we have natural log on f, this is the same here, and this is a minus sign, that means 1 and 3 are going to cancel out. And now you're asking, can't you just say the same thing about 2 and 4? Won't they just also cancel out and you'll just have this whole thing equals 0? Well, there's a slight nuance here. And let's just see a little picture here to see what I'm talking about. So here's the picture, and let's just focus on this picture just for now. We'll come back to this page in just a second. So what I've drawn here is a bunch of points, and I've labeled them f sub 0, f sub 1, and so on. These are just going to be points evaluated, f evaluated at certain points. So f naught, or f sub 0, is going to be the first point, the initial point of our f. And we represented that here by z naught plus r e to the I 0, or z naught plus r. Okay, so that's going to be our starting point, f naught. Now, let's say we go a little bit further. We go to f sub 1, and let's say that's right here. Well, the angle has changed, right? Because the angle used to be 0 here with a positive real axis. Now the angle has increased a little bit. Now let's say we go to a further point, f sub 2. Now the angle here has increased even more. Let's say we go to f sub 3. Angle increasing more. Angle is increasing. Angle is increasing. Angle is increasing with f sub 6. And now when we go to f sub 7, we see we've again crossed the real axis. So what does that mean? If the angle was initially 0, as we're going, after we get past f sub 6, at some point, we're back at 2 pi. So the angle is now 2 pi, okay? So now if we go to f sub 7, the angle is greater than 2 pi. I've put all the these points in green because they're occurring at angles that are greater than 2 pi. So this is an angle greater than 2 pi. This is again greater than 2 pi. We just keep going. We just keep going like this. These are all positive. F sub 10, and then I've written the last one as F sub n, which is going to be our ending point. So let's note something about the ending point. The ending point is indeed the same as the beginning point because it's a closed loop. We can't do anything about that. The ending point and beginning point are the same point, but their angles are going to be different. And let's see what that means, because as we go to F sub 10, as we go back to F sub n, we have completed 2 full rotations. We completed 2 pi once, we completed 2 pi twice. So we've actually completed 4 pi. So what's the angle at the ending point? The angle at the ending point is 4 pi. What's the angle of the beginning point, F naught? It's going to be 0. So actually we've completed 2 full revolutions, and even though the ending point and the beginning point are the same, how do we know they're the same? Let's go back to this page really fast. The ending point was the f of this number, and the beginning point was this number right here. And this number right here, as epsilon goes to 0, becomes z naught plus r e to the I 2 pi. And again, we showed right here, that's why 1 and 3 cancel out, because the beginning point, and the ending point are the exact same. But the slight nuance here is that their angles are not the exact same, because we see that by making revolutions like this, their angles are continually changing. So even though the moduli of f naught and f sub n are the same, their angles are not going to be the same necessarily. Okay, they could be the same, and the only way they would be the same is if we did something crazy like the loop started going around, and then the f sub whatever started coming back and went back to the same angle. Okay, so what we have is that 1 and 3 cancel, so we put crosses, we cross them out, but 2 and 4 become what? So it becomes, we're going to factor this I out from both, and we're going to have I times theta of f of z naught plus r e to the I 2 pi minus epsilon minus theta at the angle at f of z naught plus r e to the I epsilon. Okay, so we see that we have this right here, and this is going to become what? I times the total change in theta for f of z. And again, let's go back to our picture just to solidify that knowledge. This is indeed the total change for f of z, right? And keep in mind, this is the total change for f of z, and it's not the total change for z. The total change for z we already know. The total change for z was 2 pi because we started at 0 for z. Let's go back to this picture. We started at 0 and we went around to 2 pi. That's the total change for z. But f of z, what happened while z was changing? Well, this picture shows that it changed by 4 pi. Really, it could change by any value, but we see that the total change of f here was 4 pi. So in this case, we would have I times 4 pi, and this would be the change in theta for f of z. So I've just labeled down here in purple each of these just to make it definitely concrete. So this theta right here associated with the endpoint is going to be the angle of f of z after z goes around from the start of gamma around 1 rotation. And what I've underlined in black is key, as z goes 1 rotation. But that doesn't necessarily mean theta has gone 1 rotation, right? We saw in the previous example, theta went 2 rotations, for example, or f went 2 rotations, for example. And then this theta right here is going to be the angle of f of z at the beginning of gamma, before we have even gone anywhere. And we saw at the beginning, we saw that this quantity right here was 0 for this example, but again, it need not be 0. We just need to calculate the total change. So what have we found? Okay, let's coordinate all of our knowledge. We found that this integral right here, which is what we started with, right? This integral right here is equal to I times the change in theta for f of z. So if we take 1 over 2 pi I times that integral, let's say we take 1 over 2 pi I times that integral, then we're going to have to take 1 over 2 pi I right here. And then these two i's will cancel out, this I being in the numerator, this one being in the denominator, and we're just left with 1 over 2 pi times the change in theta for f of z. So again, that's what we have down here. We have 1 over 2 pi times the change in theta for f of z. And this is actually really good that it has a 1 over 2 pi, because the change in theta is going to be measured in terms of 2 pi. Because as in the previous example, with this example, we had change in theta was 4 pi. So 4 pi over 2 pi is 2, which represents how many rotations we've done. So really this quantity underlined in black is how many rotations we've done. But wait, we're not done yet. So we've calculated that integral right here. But remember, we calculated that integral in the beginning of this video as a different quantity. We calculated this quantity right here, this integral quantity divided by 2 pi I, as the number of zeros in gamma minus the number of poles in gamma. So the beautiful thing right here is that we can cancel out this integral. We don't even need to worry about it, because since we have two equivalent quantities, we can equate these quantities to each other. So we no longer have to worry about integrals. And we can just say that the number of zeros in gamma minus the number of poles in gamma is equal to 1 over 2 pi times the change in theta for f of z as z goes around 1 full rotation around gamma. And that is pretty neat. So we're going to be using that in a, in an example right now, and then the next video will be on a few more application. So here's our example. We want to find the number of zeros of f of z equals z cubed minus 3z plus 6 in the first quadrant. So the principle we just derived right here, this is called the argument principle, by the way, which is what this video is titled. This is called the argument principle, specifically that number of zeros minus number of poles equals 1 over 2 pi times the change. That's known as the argument principle. We have that this principle tells us how many zeros. It doesn't tell us what the zeros are, but it tells us the next best thing, how many zeros there are in any certain quadrant or sector of the plane that we want. So in this case, we're interested in the first quadrant. So we want to pick a gamma that lies only in the first quadrant. So we've picked the gamma that starts at the origin, goes to some value r, it goes around the quarter circle of radius r up to IR and goes back down to 0. Okay, so it's consisting of 3 parts, gamma 1, gamma 2, gamma 3. So what's our task? The general task in these kind of problems is to try to figure out, you want to try to figure out the number of zeros, because see, the point is number of poles doesn't matter, because this function has no poles, right? So we already know right off the bat that number of poles is 0. So that means that number of zeros equals 1 over 2 pi times the change. So if we want to find the number of zeros in gamma, and as you might have guessed, we're going to take this gamma, this r to go to infinity, so that this is going to become the entire first quadrant. If you want to find the number of zeros in that first quadrant, you need to find 1 over 2 pi times the change in theta for f of z. So the thing we're interested in finding now is this. We want to find the change in theta for f of z. And that's what we're going to do for these 3 parts of gamma. So let's do it for gamma 1. So on gamma 1, what happens? On gamma 1, this is all just real numbers, right? What happens when you plug real numbers into this function right here? What kind of values does a function take? Well, if you plug in real numbers into this function, you're only going to get real numbers back, correct? And real numbers have theta what? Real numbers all have theta 0, because they all lie on the real axis, which has theta equal to 0. So that means that we say that on gamma 1, f of z remains real, so change in theta as we travel across gamma 1 is 0, because we're never leaving the real axis for f of z. So that's easy. Now, gamma 2 is probably the hardest to compute. So gamma 2 is what? We have to parameterize it. We have to say it's r e to the it, but as t goes from 0 to pi over 2, because it's going from 0 to the angle just pi over 2, not the full circle or half a circle. So f of z is equal to f of r e to the it. I just plugged in this gamma 2 into z. So now this is what? Now we plug in this r e to the it everywhere we see a z in this formula. And we get r cubed e to the 3it minus 3r e to the it plus 6. Now what we're going to do, this is basically common practice, what you should do. You factor out r cubed e to the 3it. So I factor that out, and this term becomes a 1. This term becomes a 3 over r squared e to the 2it. And this term becomes a plus 6 r cubed, plus 6 divided by r cubed e to the 3it. Now let's see what happens. Now we want r to approach infinity, right? That's the ultimate goal. We want r to approach infinity. So as r approaches infinity, look at this quantity in parentheses right here. What's going to happen? This bottom denominator and this bottom denominator get huge, which means these terms basically cancel out, and this whole parentheses term just goes to 1, which is the constant term here. So we're going to have 1 times r cubed e to the 3it. So we said the part in parentheses approaches 1. And we say that f of r e to the it, which is this whole term, parentheses times this term right here, goes to just this term right here, times 1, which is just that term right there. So we see that as r approaches infinity, this term dominates. It takes over, and these other terms right here don't matter. Okay, so now we're going to say it just approaches this term right here. And what is the angle of this term right here? So we want to find out what's the angle of that right there. Well, how to do that is, let's take that term right there, and we're going to expand e to the 3it in terms of cosines and sines. So it's going to be r cubed times cosine 3t plus I sine 3t. Remember, we can expand e in that way. And we're going to, again, factor everything out. So we're going to expand out rather. We're going to do r cubed cosine 3t plus r cubed I sine 3t. So now what you're dealing with is this complex number. So this part is real, r cubed cosine 3t. So pretend that's here. That's the real part. And the imaginary part is r cubed sine 3t. Pretend that's up here. So then you have the imaginary number. It's just lying right there. Now, what's this angle? Again, we're interested in that angle. So if we were to, we could do an elementary calculation to find that angle, and let's just do it. So what is the horizontal component? It's going to be r cubed cosine 3t. The vertical component is r cubed sine 3t. So if we take vertical over horizontal, we get r cubed tan 3t tan 3t. Actually, we don't, the r cubed cancels out because it's r cubed over r cubed. So we just have tan 3t. And we want to find the angle. So we would take inverse tangent of that. What's the inverse tangent of 3t? It's just going to be 3t. So we found the angle theta is equal to 3t. And we see that this is a variable angle, but that's good because we want this angle to vary to get anywhere with this problem. So we see that as t goes from 0 to pi over 2, what happens to 3t, which is the angle? It goes from 0 to 3 pi over 2 because 3t is just multiply all these t's by 3. So we see that the angle here, as we travel from right here around the circular arc to IR, the angle changes by a value of 3 pi over 2. So you see that the change is going to be 3 pi over 2. So far, we have the change is 0 for gamma 1. The change is 3 pi over 2. So our running total for the change right now is 3 pi over 2. Now let's see what happens on the final path from IR back down to 0. Okay, so on gamma 3 of t, gamma 3 of t is what? Equals IY, where you can plug in real values for y. So first y is really, really big, right? It's up here somewhere. Then y gets small, 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 and goes to 0. That's exactly what gamma 3 is. So we say our y goes from r to 0. Okay, so let's go ahead and plug in IY as our z right here to get to shed some light on what this is going to be. So I plug in IY everywhere I see a z here. I'm going to get IY cubed minus 3IY plus 6, and I'm going to rewrite this as negative IY cubed minus 3IY plus 6. And now what's the real part of this? It's going to be just 6. What's the imaginary part? It's going to be negative y cubed minus 3y. And notice that the imaginary part is always less than 0. And why is that? Because y is always positive, right? It's always either up here somewhere or 0. So it's either positive or 0. So we see that this is always less than 0, because if we have this negative number here and we make it even more negative, it's just going to be negative. So we have that imaginary part is negative and the real part is always positive because it's just a constant 6. So what does that mean for us? Well, we can illustrate that kind of graphically. Let's just do a little bit right here. So pretend this was our graph of f, right? So f starts at 0, and on gamma 1 it has a total net change of 0, so it's still here. Now on gamma 2 it has a total net change of 3 pi over 2, so now f is here. Now what happens? So we're on this line here, and then we're starting to traverse gamma 3. On gamma 3, f begins where? So it starts where this imaginary number here is really, really big, and this real number is 6. So if we have this real number is 6, pretend 6 is right here, and this imaginary number right here is really, really big, that means it's a really, really big negative. It's going way down here. Let's just pretend it's down here. So what's the angle that this dot right here forms with this? It's going to be a really shallow angle right here. That's going to be really close to this 3 pi over 2. And as technically this is going to infinity, it's going to be at 3 pi over 2. And then as y approaches 0, then this angle, this imaginary number goes to what? Well, the imaginary part goes to 0, and the real part goes to 6, which means that f is approaching the just 6, which means that it's going up higher till it gets to 6. So it's doing what? It's going from 3 pi over 2 to, and it's traversing an extra 2 pi, so it's going to 2 pi, because 3 pi over 2 plus 2 pi plus pi over 2 is going to be 2 pi, okay? So let's see in total what's happened to our angle. First it's at 0, then it goes to 3 pi over 2, then we just saw it goes to 2 pi. That's total change of how much? That's going to be a total change of 2 pi. And now let's look at the argument principle to tell us what to do. So we see that if we have the total change, which is 2 pi, we divide it by 2 pi. So now the total value of this black underlined is going to be 1. That's going to be the number of zeros in gamma minus the number of poles. But we established number of poles is 0. So that's the number of zeros in gamma. So what we have found, and we have taken r to go to infinity. So in fact, this curve right here is going to be the entire first quadrant. We found that there's 1 0 for this this equation right here in the first quadrant, and we've done that using complex analysis and just using change of angles. No integrals involved at all. So that's kind of the beautiful thing about the argument principle, and we'll see application of it in the next video.